Today I'm going to solve the first problem in electric field. The question is the following. There's a charged rod, positively charged, which is along the x-axis. And the length of the rod is A, and the charge of it is equal to Q. Okay? And the question is, what is the electric field at this point P? Maybe I should use another color for that. Yeah. So let's remember the formula for the electric field in general. So the electric field for a single charge is equal to 1 over 4 pi epsilon 0 Q divided by R squared, right? So Q is the charge and R is the distance. What we're going to do is we will use the idea that is coming from calculus, right? What we're going to do is we will take a small part of this charged rod and then calculate the electric field due to that small part, and then add all these small parts, which is basically a continuous addition or integration, right? So that's basically how it goes. Okay, so let's draw it again. So this is the picture, and I'm going to take a small part of this. Small meaning it's infinitely small or infinitesimal, right? So that's where the thickness of this is dx, right? And because it's infinitely small, the charge of this thing is dq, okay? And it's along the x-axis, and I would like to calculate the electric field due to this small charge dq, okay? And the total length was a, and also this distance, I can give it as L, okay? So again, the question is, what is the electric field as a function of the length of the sky, A, and also the direction. The direction is obvious, it's pointing towards the x-axis, and as a function of A, L, Q, and obviously there will be factors like pi and epsilon 0. Okay. So let's go back. So what I want to do is I want to find out the electric field due to this dq at this point P, right? And I know that the total length is L, and what I'm going to do is I'm basically going to take this distance and any arbitrary distance. It's located at an arbitrary distance of x, okay? And I would like to find out the electric field due to this dq if it's located at a distance of x away from the y-axis. So remember that this is y-axis and this is x-axis, right? And then what I'm going to do is I'm going to calculate the effect of this and add them up from the initial point, which is located at x is equal to 0 up until where x is equal to a, right? So that's the idea. Okay, so let's do it. The electric field due to this small guy dq, I'm going to call that dE. dE stands for infinitely small electric field, and obviously it's a vector, so that's why I'm putting an arrow on top, and that's equal to the same factor, right? 1 over 4 pi epsilon 0. And then I'm going to have, instead of q, I have a small charge, which is dq, divided by the distance, which is the distance from all the way up in here to here. So remember that the total distance is L, and this is x, so the remaining part is equal to L minus x, right? Okay. So the distance is L minus x squared, right? And it's pointing towards this direction, so I'm going to write I hat. Okay, so that is the electric field due to this dq, and I can even highlight this small part, okay? And what I'm going to do is, again, we will add all these small guys from here to here, and that's going to be the whole electric field due to this rod, right? So let's do that, and we do it by using integration, right? So that is equal to dE, and that's equal to electric field basically add all these small contributions due to each of these charges. And each of them will be different because they're all located at different position x, right? So x changes when you go from here to here, from 0 to a. So what is that equal to? That's equal to, let's write down the term. So that's this guy up in here, 1 over 4 pi epsilon 0 dq divided by L minus x squared, okay? And I hat is outside, right? What I want to do is I want to integrate it. I want to integrate means take the sum, take the continuous sum from here to here. Here, the thing that changes is x, right? But I have dq here. How am I going to take the integration? Like, how am I going to integrate that, right? So in order to do that, so we have to ask the following question. What is dq, right? So that is the question. So dq is the infinitely small charge. So I can write it down here. Charge of an infinitesimal part of the rod, right? So that's what dq is. So let's add this guy, right? So what is that equal to? So it is equal to the following, right? If it's one, so this problem, remember, is one-dimensional, right? It's just it's along one line. So that's why for one-dimensional, and we're assuming that it's thin enough. So it's not thick; its thickness is small. For that, in one dimensions, the charge is equal to infinitely small charge, or any charge. It's charge density, which is charge per unit length. Let's write it here. Length times length. Right? So it's pretty simple. It's charge per unit length times length is equal to charge, right? That's very simple. So in terms of math, dq, infinitely small charge, is equal to charge per unit length. We usually label that with lambda. Lambda stands for, again, charge per unit length. We multiply that by the length of this thing. What is the length of this guy? It's dx, right? So that's dx. And what is charge per unit length, particularly for this problem? It is the total charge q divided by the length of that, the total length of that, which is a. So it's q divided by a, multiplied by dx. This is obviously in 1D. If you are working in 2 dimensions, this problem isn't a 2-dimensional problem, but let me state it, so that we have an idea what happens. It's charge per unit area, which we usually, represent by sigma. Sigma stands for, now it's 2-dimensional, so that's why instead of charge per unit length, which in general we can call it charge density if you like, charge per unit area times the area of that small portion. If it's a surface, if it's 2-dimensional, it's the area of that small, infinitely small surface. In 3D, it is actually, normally if it's 3-dimensional, it should be more complicated, right? But in here, it's actually not, because it's the thing that you already know. Charge per unit volume, which is rho, that stands for density, multiplied by the small density of that infinitely small portion of whatever we're considering. So this is actually a more, so to speak, familiar thing from mass, right? It's rho times dV, or density times volume is equal to mass. So for some reason, people basically, have an idea about 3D, and they have some people have difficulty in, seeing this. Okay, so that's 1D. So this is extra, right? This has nothing to do with this problem. I'm just giving this as an extra info, which we will use in other questions that I'm going to solve later. Okay, now going back to this problem, this is q divided by a times dx. So instead of here dq, I can write this as integral is I 1 over 4 pi epsilon 0. Instead of dq, I'm going to replace that by q divided by a times dx. And that's dq, and I still have another term in here, right? 1 over L minus x squared. Okay, now and let me even take the constants out of the integral, right? Q is constant, I'm going to take that out. 4 pi epsilon 0. I'm going to take that out as well. And A is constant, right? These are all constant. A, remember, is the length of this rod, which doesn't change, right? It's constant. So now the integral is basically the following. I have dx on top, and here I have L minus x squared. X is the variable, and I know how it changes. The initial position of the x is 0. It starts from here, right? And then once you reach the end of this rod, it becomes a, right? So the range of the integral is from 0 to a. Now I have to take this integral. It's an easy integral, right? The way to do that, these kind of integrals, is very simple. You just make a change of variable because, you know, since L is constant, you can just replace L minus x by another variable, which I'm going to do here. Maybe I should do it with another color, right? Let's call L minus x equal to u. Let's make that change of variable. And if that is true, if I take derivative of both signs, right, the derivative of L is 0, and that's why it only hits here, so that's minus dx is equal to du. So the integral here, I'm going to call that 1, becomes, after I make this change of variable, right, the following. I had q divided by 4 pi epsilon 0, and there's another term a here. And let me go back and show you the range of the integral. It was from 0 to a. Since I'm now changing the variable from x to u, when x is equal to 0, so let me write it here. When x is equal to 0, you can see that L minus x becomes L minus 0, which is L. When x is equal to a, you see that L minus x becomes L minus a. So the range of this integral becomes from, initially it's at 0, which is L. Finally, it's at L minus a, right? Okay, and inside the integral, instead of dx, you can see that dx is equal to minus du. Since minus dx is equal to du, dx is equal to minus du. So that's minus du divided by, I have L minus x squared. Remember that L minus x is equal to u, and that's why this becomes u squared. So now this is a simple integral, right? So you have minus 1 over u squared integral is equal to 1 over u. So let me write it here if you like. So minus the integral of the u over u squared is just simply 1 over u. And now I can simply integrate that. That's I hat again, q divided by 4 pi epsilon 0 a. Now I have this term which is 1 over u. Remember that the range of this integral is, the initial one is L, and the final one is L minus a, right? And if I do the math, so it's I hat q, all of these terms again, 4 pi epsilon 0 times a, and if I put the upper 1, that's 1 divided by L minus a, minus, if I put the lower one, it becomes 1 over L. Now I have to equate the denominators, and I'm going to multiply this by L and this by L minus a, right? And if I do that, this becomes I hat q divided by 4 pi epsilon 0 L minus L minus a, all divided by L times L minus a. So you see that this cancels that, and minus and minus cancel each other, and you get plus, right? So at the end, so I'm going to take it with a star. The final result, the star is equal to, so the total electric field at point P, let's say, is equal to q divided by 4 pi, and there's extra a that I forgot here, 4 pi epsilon 0 a, and on top I have plus a, and on the bottom I have L times L minus a. You see that this a cancels the other a here, and there's an I hat here. So I should write the final result here. So E at point P is a vector that's equal to I hat Q divided by 4 pi epsilon 0 L times L minus A. Okay, so I hope this is clear, but we can actually, there's a nice thing in physics, right? We can actually look at this final answer and take the limit, take an asymptotic limit in quotations, which means like if you take this P very, very far away from this rod, what's going to happen is, just imagine yourself sitting at P, and if you look at this rod, what will you see? You won't see a rod or something. You won't even see anything. You will just see a small dot, like a point, right? So that means if you take the limit when you're far away from this rod, which corresponds to L being much bigger than A, then this result becomes Q times 1 over 4 pi epsilon 0. L, when L is much bigger than A, this becomes L, and you have another L here. So it will simply be 1 over 4 pi epsilon 0 Q divided by L squared. And it is exactly this initial formula which is given for a single charge Q, right? And it makes sense, right? Because if you're far away from this rod, you won't even know that it's a rod. You will see as if it's like a single point-like charge. And for that, I know the formula, and this gives exactly this formula. So in physics, you can always take these asymptotic limits and look at any problem this way. And this is a very important skill where physicists teach during these courses. Okay, thank you.